Hello and welcome to this quick review introducing haloalkanes. Before you begin, it's worth making sure you've got your independent study notes or your notes you've completed on them before watching the clip, and have these in front of you as we go along. So if we think about what the word haloalkane means, obviously halo means that it contains at least one halogen atom bonded directly to the carbon chain or ring of a saturated hydrocarbon, being an aliphatic or alicyclic compound. So naming straight chain and branched haloalkanes is quite easy, because all you do is count the carbon atoms according to how close they are to the halogen atom. So I've highlighted one of them for you to give you the idea. So here's a little exercise for you. See if you can, on a piece of paper perhaps, put down the names of these haloalkanes. But draw them out first, obviously. Maybe add it to your notes, perhaps. So pause the clip and see what you can do. And you can resume the clip when you've finished. So hopefully you got something similar to those ones there. Now these were a bit more complicated than the ones you might see in textbooks or exam questions. So it's worth thinking about how we did it. So it's a good time to introduce the idea of locant numbers. So you've been doing this all along since you started doing basic organic chemistry, but may not realise that what you're referring to is the locant number. All the locant number is the number that we assign the carbon in a chain or a ring. And obviously, when we look at a functional group or a branch or whatever, we may have to make a decision about which end of the carbon chain has the most branches, or which end of the carbon chain has the halogen atom attached or the alcohol group attached or whatever. So what we try to do is make sure that the locant number is always as low as possible. And what you may have come across instead of that idea would be the idea of looking at the carbon where the functional group is located. And that's going to be the end that you count carbon 1, 2 and 3 from. So for example, the one on the far right is going to be 2-bromobutane, not 3-bromobutane. So when you classify haloalkanes, what you've got to do is consider the carbon atom that the halogen is bonded to, which I've now highlighted on each of these examples. So if you have one alkyl group attached to the carbon the halogen is bonded to, then it's called a primary haloalkane, in exactly the same way that alcohols are classified. If you have two alkyl groups, it's then called a secondary haloalkane. And likewise, if you have three alkyl groups attached, it's called a tertiary haloalkane. And if the halogen atom is directly attached to a ring, we then call this a secondary haloalkane as well. So here's another exercise for you. See if you can pause the clip, and on the piece of paper you've used a few minutes ago, now you can classify those three examples. So using the classifying system we've just covered, in 2,4-difluoro-2-methylpentane, it's tertiary on the locant number 2, but secondary on locant number 4. In 2,2-difluoromethylcyclohexane, both halogens are on secondary positions because they're attached directly to a ring. And in 2-bromobutane, it's quite straightforward. You have an ethyl group on one side, a methyl group on the other, part of a carbon chain of 4, so therefore it's secondary to bromobutane. So if you think back to some previous organic chemistry that you've done, you'll see that there's several ways of making haloalkanes. But they don't just come from the halogenation of alkenes, as you can see. You can also make them by radical substitution. So it's worth remembering the different ways in which haloalkanes can be synthesized. So it's worth remembering these two methods because they may come up in exams quite often. So it's also time to introduce a brand new mechanism. Not brand new if you're a second year perhaps and looking at this as a review, but if you're a first year, you might not have come across this mechanism before. But nucleophilic substitution is the way that haloalkanes actually work. So it's worth pointing out a few things that you need to be aware of. So nucleophiles are species that possess a lone pair of electrons that they donate to form a data covalent bond. So in this case, the hydroxide ion is acting as a nucleophile. And because it's also negatively charged, it's repelled by the partially negative chlorine atom. So like it says, it attacks through the back of the carbon rather than coming around from the front. So you can see the curly arrow points around the back of the carbon. So don't forget you need your dipoles to get marks in this as well, and you need the correct products including the chloride ion that's been substituted. So if we consider this particular mechanism, if we're using OH- as the nucleophile, to also be a hydrolysis reaction, that means that the rate of the hydrolysis depends on the carbon-halogen bond enthalpy. So the first thing that has to happen is the carbon-halogen bond has to break. So if it takes less energy to do that, then the reaction will happen more quickly. So the halide ion that is released as a side product can be tested for. As you probably remember, the test for halide ion is a silver nitrate solution. And you get a silver halide precipitate, so in the equation at the bottom, X represents either fluoride, chloride, bromide or iodide. And the speed with which this happens can be recorded, so therefore the quicker it happens, the more likely it is that the bond enthalpy is quite low. And obviously you can use the colour of the precipitate to confirm if it's silver iodide, silver bromide or silver chloride that's being formed. Okay, so it's now time to have a go at a quick exam question. So this is a simple example of an A-level question where it has a little bit of work with haloalkanes, but also a little bit of other work on percentage yield. It's quite common to have more than one topic coming up together. So if we have a look at it, it says the student reacted 8.72 grams of bromobutane with an excess of OH-, very similar to the thing we've looked at just now. The student produced 4.28 grams of butan 1-ol. And in this reaction, the hydroxide ion is acting as a nucleophile, just like we've discussed. So this type of reaction, if you're going to substitute one group for another, that's then called a substitution, not surprisingly. And like we talked about earlier, a nucleophile is any species that has a lone pair of electrons that can be donated to a data covalent bond. So the next part asks us to outline the mechanism for this reaction. Obviously this is the nucleophilic substitution mechanism that we've just talked about in this clip. So I'm going to move the page down a bit to make some room for that. So it asks us to show curly arrows and relevant dipoles. It's very important to follow that instruction because quite often when we're marking past paper questions and tests that students do, for mechanisms they often forget to do that even though it's printed right in front of them. So make sure you read that and take it on board and incorporate it into what you're doing. So you'll notice that in the question it says bromobutane but it doesn't say exactly where the locant number is. But it does tell me that my product is butan 1-ol. So I'm going to put the bromine on the first carbon, so it's 1 bromobutane I'm going to use. So notice how what I've done is I've taken my curly arrow and drawn it around the back of the carbon like we talked about earlier. Why do we do this? It's because just like before, the bromine atom is slightly negatively charged, so that's going to tend to repel the negatively charged OH. So the actual OH moves in behind and attacks that way. So now what can happen is that the carbon-bromine bond can break. Bromine is more electronegative than carbon, so the bond pair goes on to the bromine. And that means the OH now bonds to the carbon via the oxygen atom, so that gives us butan 1-ol, and not forgetting, of course, our bromide ion. So, next thing to do is to go down to part 4. Again, I've got to move the page down slightly in order to do this. So it says calculate the amount in moles of CH3, CH2, CH2, CH2Br reacted. Now to do that, we've got to go back to the beginning of the question and see how much actual bromobutane we have. So whipping the page down very briefly, you can see you've got 8.72 grams. So by signposting my calculation by saying the number of moles of bromobutane is 8.72 grams over 136.9 grams per mole to the minus 1, I'm basically doing moles equals mass over molar mass, that gives me 0.064. The next part of the question asks you to calculate the amount in moles of bromobutane, butan 1-ol. So let's now go back to the beginning of the question and see if we can find out how the mass of the the mass of the butan 1-ol is. So we produced 4.28 grams of butan 1-ol. So that gives us, doing the same calculation this time, 0.0578. So the percentage yield is obviously the actual moles we obtain over the theoretical moles that we should have got times 100, which is 0.0578 over 0.064. Obviously it's a 1-to-1 mole ratio between butan 1-ol and 1 bromobutane. So that gives us 90.3 as our percentage yield. Okay, so that takes us to the end of this clip. Hopefully it's been a fairly useful introduction into how to do haloalkanes, or how to have a think about them. And for now, thank you very much, and until next time, see you soon.